Here are 9 boxes in a row. Some of them share a color. Count them. 2 boxes of color 1 at the far left and far right, 3 boxes of color 3 scattered through the row, 3 boxes of color 2 bunched together in the middle, and 1 lone box of color 4 all by itself. The rule is simple. Pick a group of neighboring boxes that are all the same color, remove them, and score the size of that group squared. Do that until every box is gone, and add up your score. Watch what happens if you always grab the biggest matching group you can see right now. 9 points for the 3 2s, then 4 points when 2 of the 3s end up sitting next to each other. Then the last 4 boxes, 1 point apiece. 17 total. Now watch this. Same 9 boxes, same rules. I'm just going to remove 1 box, a different one, first. 9 points. Then 1, then 9, then 4. Total, 23 points. Same boxes, same moves available at every step. 6 points higher, over a third more, just from choosing a different order. That gap is the entire problem. By the end of this video, you'll know exactly why removing the wrong box first can be the only way to win, and you'll have a method that finds the best order every time, guaranteed. This problem is called remove boxes. Formally, you're given an array of positive integers, where each number is a color. At each step, choose any run of adjacent boxes that are all one color, remove all of them at once, and earn points equal to the size of that run squared. Not the size squared. Keep removing runs until no boxes are left. Your score is the sum of every removal. The question is, what's the maximum score you can possibly reach? Squaring is what makes this interesting. Removing 4 matching boxes together is worth 16 points. Removing them as 2 separate pairs is worth only 8. The reward for combining grows much faster than the group itself. That's why it can be worth walking past a match, clearing something else out of the way, and combining it with a match somewhere else entirely. Your first instinct might be greedy. Always remove the biggest matching group available right now. The 9-box example already broke that. The winning move was to remove a single isolated box that didn't score much by itself, purely to set up a bigger merge 2 steps later. Greedy can't see that far ahead. Your second instinct might be, fine, no greedy, just try every possible order with recursion and keep the best one. That works. It's also so slow, it's useless, and understanding exactly why is the first real step toward the actual solution. Let's shrink the problem down to 3 boxes. Color 1, color 2, color 1. Just 3 boxes, 2 colors. Option A, remove them one at a time, left to right. Box 1 alone is worth 1 point. Box 2 alone is worth 1 point. Box 1 alone again is worth 1 point. Total, 3 points. Option B, remove the middle box, the color 2, by itself first. That scores 1 point, but now the 2 color 1 boxes, which used to have something between them, are sitting right next to each other. Remove them together. 2 boxes squared is 4 points. 1 plus 4 is 5. Option B beats option A 5-3, using the exact same 3 boxes and the exact same rules. Notice what actually happened. The middle box wasn't valuable to remove. It only ever scores 1 point no matter when you take it. Its real job was to be an obstacle. Removing it early wasn't about the points it gave you directly. It was about what it unlocked. That's the whole idea of this problem in miniature. Some removals are worth more for what they connect than for what they score. So let's just try everything. At every step, look at the array, list every group of matching adjacent boxes you could remove right now, and recursively try each one. Keep whichever full sequence scores highest. This is correct. It will always find the optimal answer because it genuinely considers every possible order. The problem is speed. If you have n boxes, all different colors, then at the top level you have n choices for what to remove first. After that, n-1 choices, then n minus 2. The total number of orderings is n factorial. For 10 boxes, that's already over 3 million orderings. For 20 boxes, it's past 2 quintillion. More orderings than there have been seconds since the Big Bang. LeetCode allows up to 100 boxes. Brute force isn't just slow here, it's not finishing this century. The standard fix for a slow recursion like this is memoization. Notice when you're solving the exact same subproblem twice and cache the answer instead of recomputing it. For a lot of array problems, the natural subproblem is just the boxes from index L to index R. Solve every contiguous subarray once, combine the answers, done. That's exactly the move that works for problems like matrix chain multiplication or burst balloons. It's the obvious next step here too. So let's try it. And watch closely, because it's about to fail in a very specific and very informative way. Let's define dp of L, R as the best score obtainable from just the boxes between index L and index R on their own. If this quantity is well defined, if it truly only depends on L and R, we can build the whole answer by combining subarray answers, and we're done in polynomial time. Here's the array that breaks it. 3, 2, 1, 4, 4, 2, 4, 4. Look at the very first 3 boxes. 3, 2, 1. No repeats in there. On their own, there's only one sensible way to clear them, worth 1 plus 1 plus 1, 3 points, and dp of that subarray looks like a fixed number. But look at what's later in the array. 2 separate groups of 4, 4, with a lone 2 sitting between them. If we clear that lone 2 first, the 2 groups of 4s become one group of 4 4s in a row, worth 16 points instead of 8. Now focus on just the first pair, the 2 4s sitting at positions 3 and 4 on their own. As their own 2-box subarray, the best you can do with them is remove them together. 2 squared, 4 points. So dp of that subarray is a perfectly well-defined number. It's 4. No ambiguity there. But the globally optimal plan for the whole array does not cache that pair in for 4 points. It holds them, unremoved, waiting, while the lone 2 gets cleared out of the way somewhere else entirely. Only then does it combine all 4 4s into one group for 16. The best global strategy deliberately refuses to take the subarray's own best local score. That's the real problem. It's not that dp of LR is undefined. It's that even where it's perfectly well-defined, it isn't safe to just add into a bigger sum. The globally optimal plan can require a subarray to sit there holding a smaller score than it's capable of, purely because something better is coming from outside it. And whether that's worth doing depends on a fact dp of L, R has no way to represent, how many matching boxes are waiting out there, and whether it's worth pausing for them. 2 dimensions aren't enough. We need a third one, and it needs to capture exactly that missing fact. How many boxes matching the color at the right edge are out there waiting to be attached? Here's the fix. Define dp of L, R, K to be the maximum score obtainable from boxes L through R, given that there are K extra boxes of the same color as boxes at position R, waiting just past the right edge, ready to be merged in whenever we like. Picture it as the subarray boxes L through R, followed by K faded ghost copies of whatever color sits at position R. Those ghosts aren't literally still in that spot in the original array. They represent a promise. K boxes of a matching color are reachable and can be pulled in before position R is finally dealt with. Now, for any state dp of L, R, K, there are exactly 2 sensible strategies, and the optimal score is the better of the 2. Strategy 1. Remove now. Take the box at position R together with all K of its waiting matches as one single group of size K plus 1. That scores K plus 1 squared. Then solve whatever's left. boxes L through R minus 1, with 0 extra waiting boxes since we just used them all. Strategy 2. Delay and go find another match. Scan leftward for some earlier index I, strictly between L and R, where boxes at I is the same color as boxes at R. For each candidate I. First, clear out everything strictly between I and R. That's dp of I plus 1R minus 1 with 0 waiting boxes, an independent clean subproblem. Clearing that gap makes boxes I and boxes R adjacent. Now box, I effectively has K plus 1 matching boxes trailing it, the original K plus box R itself, so the rest of the score is dp of L, I, K plus 1. Take the best over every valid I, and the best of that against strategy 1. That's the full recurrence. dp of L, R, K equals the max of dp of L, R minus 1, 0, plus K plus 1 squared, and for every I where boxes I equals boxes R, dp of L, I, K plus 1, plus dp of I plus 1, R minus 1, 0. Go back to the 2 4s that broke the old notation. There, dp of that subarray was stuck at 4, with nowhere to record, and 2 more are waiting. Now it becomes dp of 3, 4, 2. And this time strategy 2 can fire. Match the second 4 against the first, collapse the gap, and let the recursion bottom out on one box carrying 3 waiting friends. 4 squared, 16. The number we actually wanted, because now there's a K to carry the fact that made it possible. The base case is a single box. dp of L, LK is just K plus 1, squared. One box plus its K waiting friends, and the only thing to do is take them all together. And the answer to the whole problem is dp of 0, n minus 1, 0, the full array, with nothing waiting outside it, because there's nothing outside it to begin with. Let's go back to the 9 boxes from the very start of this video, 1, 3, 2, 2, 2, 3, 4, 3, 1, and see the algorithm actually produce that 23. The 3 middle 2s have nothing worth waiting for, no other 2s anywhere else in the array, so dp handles them the simple way. Remove all 3 together. 3 squared is 9 points. That leaves 1, 3, 3, 4, 3, 1. Now here's the interesting decision. There's a lone 4 sitting between 2 boxes of color 3 on its left and 1 box of color 3 on its right. Strategy 1 for that 4 would be just remove it alone, worth 1 point, and move on. Strategy 2 would be, is there any benefit to waiting? The 4 doesn't match anything else in the array at all. No other 4s exist, so there's no merge available for it. Strategy 1 wins by default. Remove the 4 alone. 1 point. That leaves 1, 3, 3, 3, 1. Now all 3 3s are already adjacent, so dp again removes them as one group. 3 squared. 9 more points. Finally 1, 1. One group of 2 matching boxes. 2 squared, 4 points. 9 plus 1 plus 9 plus 4. 23. Exactly the score from the clever ordering we saw at the start. And this time, we didn't guess the order by eye. The recurrence found it automatically, because at every step it was comparing remove now against wait for a match, and always taking whichever one actually paid off. 2 things worth being careful about here. First, it's tempting to think, now that we understand the trick, that we could have patched dp of LR directly. Just remember how many matches are waiting as some kind of side note without a real third dimension. But that waiting count isn't a constant fact about the subarray. It's different depending on which larger problem the subarray is being used inside. The only way to correctly account for every possible value it could take is to actually index by it. That's not an implementation convenience. It's required. Second, the complexity. dp of LR, K has 3 indices, each ranging up to n, So there are on the order of n cubed states. That number, n cubed, is the classic signature of interval dynamic programming, and it's tempting to assume that's the final answer, especially since LeetCode allows up to 100 boxes, a number that screams cubic algorithm intended. But filling in each individual state means scanning for every matching index I, which costs up to another factor of n. Multiply it out. N cubed states times n work each is n to the fourth power, not n cubed. The shape of the state space and the actual running time are different things, and it's easy to stop checking right after counting the states. There is a way to trim this back toward n cubed. By only ever scanning positions I whose color actually matches boxes at R using a pre-computed list per color, instead of scanning every index and checking. But the textbook version, exactly as derived here, really is n to the fourth. Worth knowing which one you've actually built. Remove boxes belongs to a family of problems sometimes called interval dynamic programming. The subproblems are always contiguous ranges of an array, and you build up answers for big ranges out of answers for smaller ones nested inside them. A close relative is a problem called burst balloons, where you pop balloons one at a time and your score depends on the two balloons currently sitting on either side of the one you pop. There, the fix is smaller. You just need to know the two boundary values just outside your interval, and those are usually just the neighboring array entries themselves. No new dimension required. Remove boxes needed something the boundary values alone couldn't give it. Not just what color is next to the interval, but how many matching boxes are reachable beyond it, a quantity that changes depending on choices made elsewhere in the recursion. That's why it needed a genuinely new dimension instead of just reading a neighboring cell. The general lesson travels well beyond boxes. When a memoized recursion keeps giving wrong answers, or won't simplify no matter how you rewrite it, the usual culprit isn't the recurrence. It's the state. Somewhere, the answer to your subproblem secretly depends on something happening outside it that your indices don't capture. Find that missing fact, promote it into the state, and the recurrence you already had usually turns out to be correct after all. Let's rebuild it fast. 9 boxes, 2 orderings, 17 points versus 23. Order matters because squaring rewards big merges disproportionately. A greedy rule can't see far enough ahead to know when to delay. Brute force sees far enough but costs in factorial, impossible past a few dozen boxes. The natural fix, memoizing on subarrays alone, breaks, because a subarray's best score can depend on matching boxes waiting outside it. The real fix, a third dimension, K, counting exactly how many matches are waiting. Turning a fact, the old notation had no way to record, into an explicit indexed one the recursion can depend on. 2 strategies at every state. Remove now, or delay, and merge with a match further left. Take whichever scores higher. Run it on the original 9 boxes, and it finds 23, the same number we only found earlier by trial and error. If you remember one thing, when a recursive idea seems almost right but keeps failing, don't throw it away. Ask what fact about the outside world your state forgot to record, and give it a dimension of its own.